optimization. Okay, so today I will talk about distributed algorithms to solve a fairly general class of M estimation problems. And by distributed, I mean that we want to perform our analytics on a network, meaning that the data are distributed across multiple nodes in multiple agents in this network. And as class of M estimation problem, I will target the so-called high-dimensional statistical problems. These are problems where the number of optimization, these are over-parameterized problems, right? Just to give you I guess a common wording here that everybody can understand. Meaning that we have more variables than data, but so the system is undetermined, but the reason why we are able to recover the information of interest is because the signal of interest or the parameter that we want to estimate belongs to a low-dimensional space, right? Think of sparsity, low rank, and so on. And our interest here is to bridge statistics and optimization in the sense that I would like to establish statistical and computational guarantees for my distributed algorithms. And the entire life motive of the talk is that if we want to do that, we need to develop a new theory, a new analysis, and that actually will also open the way to new designs, new algorithms. And the reason is that the existing literature of distributed optimization, which is a long history, like 20 years or more, is mainly focused mainly on analysis that are of pure optimization type, in the sense that they don't consider the statistical component. And because of that, these analyses are either very pessimistic in terms of predictions of the behavior of the algorithms, or they break down dramatically because of the fact that they don't capture some phenomena happening in high dimension. Okay, so and that's the reason of my title, which is basically bridging statistics and optimization. Okay, let me start first with the setting, the general scenario, so that we are all on the same page. The idea here is that we want to perform analytics, so learn, make decision from so-called networking data. Networking data means that the data are not stored in a single place, but are instead distributed across multiple nodes, machines, that are now on, I'm going to call agents in a very abstract sense. And examples are, for example, sensor networks, where each sensor can collect data, so data are generated already locally, and we cannot share this data, can move this data to a server for several reasons, because there is no server in some applications, or because of moving the data are otherwise we can, for bandwidth issue or privacy issue, right? The data, we are dealing with a large volume of data, and moving the data is not feasible. Other applications are, for example, edge computing, where the idea is to move the intelligence towards the edge of the network. And we may have different devices, heterogeneous devices connecting to multiple clouds and possibly even exchanging information to each other. Or if you want, now there is a federated learning is a hot topic. So another basically setting of interest is the so-called federated learning, when we can still have a server, and the goal here is that there are multiple workers parallelizing basically the computation, and the idea is to process information in parallel. If we want to abstract a bit these different scenarios, I would say that there are two types of network architectures that we frequently deal with. On one hand side, we have the so-called hierarchical networks. These are networks where there is a server, a master node, connected to all the other nodes in the system. In general, these are also called star topologies, right? Because this looks like a star, right? And the idea here is that the processing, the optimization is basically run by the server, and there are multiple workers helping the server to parallelize the computation. For example, the workers can compute the gradient on their own data and then share this information to the master. This system, although in the literature sometimes you can find the word distributed for this kind of for algorithms running on this system, I think that the word is not correct, because these are still centralized systems. They are centralized because there is a single node connected to everybody else. And if this node will die, the system will fall apart. So on the other hand, there are another class of distributed of networks architecture that are really distributed, so-called mesh networks. Here, we no longer have a master node, but every node is basically has part of the data and is connected only to a subset of other nodes, not to everybody else. And here the goal is to the question then, and in this talk, I will mainly focus on this kind of architecture, okay? And the idea here is that we want still to learn and perform the same analytics that we do on this type of network, possibly achieving the same guarantees. And now the question is that how can we do that now that we no longer have a single node handling everything here? And the prototype algorithm in this context is in general an algorithm where the idea is try to simulate at the level of each node the behavior of the master. And the idea is that this algorithm, any distributed algorithm in general is composed of two steps. A local computation step where you use your local information to update your estimate, and then a communication step where you need to share this update with your neighbors, and then to acquire new information that you're going to use to move to the next computation step, okay? So there are these two interleaving steps, computation and communication. This will immediately suggest that then when it comes to design this algorithm, there are clearly trade-offs, right, involved, because we don't have infinite resources. We don't have infinite computational power. We don't have infinite bandwidth. So the question becomes, we would like to understand what are the fundamental trade-offs in terms of statistical error that we can achieve. Think of generalization error if we're talking about training a neural network, can think about statistical estimation error if you're estimating a parameter and so on. And trade-off between, so let's call generically statistical error and the resources that we have, computation and communications, okay? For example, a natural question is that, can I achieve the same statistical error that I have in a system like this when, however, there is no master node? And if that is possible, what is the amount of computation and communications that we need, okay? These are the typical questions. Understanding this trade-off, in particular the Pareto curve, the best or the fundamental limits, is still an open problem. Our understanding of these trade-offs is very limited. We have results when it comes to consider only a subset of these three quantities. For example, from a pure the literature of distributed optimization is plenty of analysis when it comes to understand the computation, the computational aspect, and also if you want the communication. We know how fast these algorithms are in terms of convergence rate. We also know what are the lower bounds, so how fast they can be, and we know how to accelerate these algorithms. But all these results are only of pure optimization type, meaning that they don't capture the statistical component, meaning that they will not give us a sense of the full trade-off, including the statistical error, okay? On the other hand, and so these are basically, if you want, a subset, a trade-off between these two components. On the other hand, if you look at the literature of centralized optimization and statistics, in the last, I would say, 4 or 5 years, there have been a lot of works trying to understand the trade-off between statistical error and computation. And again, interesting results, but they lack completely of the network component. And the network component will introduce a new dimension with new challenges. For example, suppose that locally agents, each node does not have enough data to perform according to the information theoretical lower bound, right? Which means that if you use only your local data, you will not be able to achieve good statistical error. But if you count the data across all the agents, all the network, you will be able to compute, to achieve statistical consistency. So, but how can we then do that? Can we achieve this centralized statistical consistency, possibly leveraging some communications? So this shows that there is a kind of trade-off between, there is a chat between, okay, I just saw a link, between communication and samples, okay? So all these type of trade-off are still open. And the main message to you, even at this very high level, and this is, if you want, is the take-home message of the entire talk, is that if we really want to answer these fundamental questions, understanding this trade-off, we need to combine at more fundamental level these three components: the optimization part, the statistical part and the networking part. Okay, that's, in my opinion, the major message of this talk. Of course, I don't have an answer for this general question, but what I'm going to do today is to focus on a simpler question related to this trade-off. And the question is the following: the question is that I will fix the statistical error, and I will fix the statistical error to the centralized one, to the same error that a centralized system having all the data in a single place can achieve. And the question is that, can I match this statistical optimality in a distributed set on a network? And if I can do that, how much communication and computation do I need to achieve these optimal estimates? Okay, that's the question. So I fix the statistical error to the centralized one, and I ask how much computation and communication I need to achieve this error. So this is the main question that we try to answer today. Okay, feel free to interrupt me if you have questions. Okay, in order to do that, let's spend the next maybe 10 minutes on a simple problem to answer this question, which is a sparse linear regression over a network. And I will also guide you through the existing literature to show that even for a simple problem like this, we don't have a clear answer. Okay. And let me introduce the problem, and then we first the sparse linear regression in the centralized setting, and then I will explain what it means solving this problem on a network. Okay, the problem, I think you are familiar with this problem. We want to estimate a parameter theta star, and this parameter, we assume that this parameter is S sparse, meaning there are only S components different from 0. But the entire full dimension here of this parameter is D. So this is a D-dimensional vector, but only S components are different from 0. And this S is clearly much less than D, okay? In this setting, we have a branch of measurement. This is the set of all measurements that we have, which corresponds to N samples. Capital N is the total samples that we have, the dimension of this vector here. And X is the data matrix, which clearly is going to be N times D, right? And then this is the standard noise on the measurements. And let's use as a proxy for this theta star, the solution of a lasso problem, right? This is a lasso in the projected form, meaning that I'm trying to minimize a quadratic function, which is exactly the mismatch between the measurements and the prediction coming from this linear model, this quadratic function, and subject to a projection onto the L1 ball, right, to enforce sparsity. And this problem is well known, and this is a typical example of polynomial approximation, right? So this is the centralized lasso problem in the projected form. But this is not the problem that we want to solve. We are in a slightly different setting, because now in our setting, we have a network, and each agent here in the network owns only part of the data, not all the data. Not all the measurements, but only a subset of them. For example, here's the situation. This agent owns only part of this data. This other agent, another set of data, and so on. Okay. Mathematically, this means that if we go back to the model here, it means that I'm splitting basically the total vector of measurements Y in sub-blocks, sub-vectors. And each one is owned by one agent. Okay. Along with the corresponding data matrix here. So this is the model. And how can I now inject this structure, this distributed nature, into the optimization problem? It's pretty simple, because all I have to do is to take this vector Y and substitute the specific block structure here. If I do that, along with the same structure for the X matrix, I can rewrite this square exploring the block-wise structure, and then I can just rewrite in this form, right? Where now every term of the sum corresponds to one of the quadratic losses associated to the data available at agent, which means that now what's happening here is that I can interpret this term, each term, in particular the height term, as the quadratic loss associated to agent I, which is basically because I call this function Fi. And clearly this function is available only to agent I, because these data are owned by agent I only. And we are not allowed here to share data among different agents. So now this problem is no longer solvable on a network because every agent locally owns only this function, but there's a common theta parameter that we want to estimate. And by the way, just in terms of notation, I keep in mind this notation. I split the total vector n of measurements, this is the dimension n, in n samples per agent. So small n is the number of samples, is the size of this vector here, is the number of samples owned by each agent. And m is the number of machines, the number of agents, okay? I assume that the data are split equally across the agent. And so this is the setting that we want to solve. Is it clear, the model? Any question? Okay, so now let's try to understand. Yes.
So just an announcement for the participants. So if you have any question, you can just unmute yourself and ask, sir. It's completely all right. So, sir, you can continue.
Yes, please, because I don't have the chat in front of me. So if you write in the chat, I may not be able to. Of course, you can read the chat for me if you find questions there. So please.
Yeah, so in case if anyone can't ask it verbally, then they can also write it in the chat and our host will read it too, sir.
Okay, thank you. Okay, so given now this model, the question is that what are the statistical and computational guarantees that we have if you look at the existing algorithm and the existing analysis, okay? So let's see what happens, and then we try to build from the existing literature. Right now, I'll guide you through the state of the art. If you look at the problem from a let's look first at the statistical properties of the solution theta hat, which are a textbook result. Sorry, by the way, let me mention that this is an important thing, that I'm gonna study this problem in the so-called high-dimensional regime. What do I mean by that? I mean that the dimension, the number of variables that I have, is much larger than the data that I have. And not only that, we are interested in a regime where the dimension, given that the data are growing and the dimension are larger than the data, the ratio between the dimension and the data is going to infinity. Meaning that this is different from the standard low dimension statistics, where you fix the dimension d and you ask yourself, what happens if I increase the number of samples, right? Can I achieve a statistically consistent estimate? Here we are not d in the traditional statistical models, d is fixed. So we don't change the model. The model is fixed. I just sample from the same model and I have more and more samples. And I try to understand the statistical properties of the solution when I have more and more samples. Here is different. In high dimensional statistics, we are both the dimension and the samples are growing, with the dimension even faster than the sample, meaning that the model becomes more and more complex. And I want to understand what happens if when the model becomes more and more complex and data also are growing, but not as fast as the dimension. Okay, this is the typical high dimensional statistical setting. And this is going to be the setting that we will consider here. Okay, is it clear? Okay, in this setting, what are the statistical properties? Suppose that someone can compute for us the solution, okay? This theta hat. It's not possible because we are on a network, but suppose for a moment that you can do that. What we can say if we use theta hat to approximate the ground truth, theta star, the parameter that we want to estimate. Under standard statistical assumptions, I will come back on this later, this model, this theta star is so-called learnable, meaning that the distance between the solution that I get from this problem and theta star is controllable by this ratio, which is exactly the order of the statistical error. And as you can see here, this is the important quantity that you need to keep in mind. This says that even we can control the statistical error, we can make as small as we want, as long as this ratio is small O1, is sufficiently small, right? Which means that, and that's the thing to remember, that if I impose that this condition holds, I have a condition on the total sample size, which has to be of the order of S log D, okay? This is the regime that you need to keep in mind, together with this. So we are in a regime where even if the dimension is growing much faster than the data that I have, I'm still able to achieve statistically consistent estimate as long as the number of samples will grow at least logarithmically with the dimension. Okay? And this is almost optimal. It's also almost minimax optimal. It's not improvable. You can improve only by a factor S here. Okay? And this is what the theory says. Now, this is a textbook result. I'm not proving, this is still an overview of the literature. So the question now is that this is under the assumption that someone can compute this theta hat for me. But how can we compute this on a network? What are the computational guarantees that we have in this regime of interest? So now on, all the results that I'm going to mention are in this asymptotic regime where, yeah, this one. Okay, so keep in mind this regime. Okay, if I look at in order to understand what happens computationally, I need to look at the landscape of this function, right? Because I need to apply now a distributed optimization algorithm. And to do so, let's look at the property of this function. This problem is a convex optimization problem, but it's not strongly convex because the Hessian of this function, which is this matrix here, x transpose x, has dimension d times d. But the rank of this matrix here, the rank of this is basically at most n. Okay, which means that given that d is larger than n, this matrix cannot be full rank. In other words, this means that if you look at the landscape of this function here, it looks like this. There are some directions where you are carved, you are strongly convex, but there are other directions where you are flat, okay, which corresponds to the null space of this matrix. So this tells us that the function is convex, but not strongly convex. How about the Lipschitz constant of the gradient of this function, which is the largest eigenvalue of this matrix, of the Hessian matrix? And this constant the Lipschitz constants will, in this, under some basic assumptions on the data generation model, like Gaussian distributed, the Lipschitz constants of the gradient will scale with the square root of the dimension divided by n. This means that in this regime, this quantity is going to blow up. Okay? Why do we care about the Lipschitz constants of the gradient? Because we are talking about, we have in mind distributed algorithm using gradient information, and any of these distributed algorithms is gonna have a step size, and the step size will be bounded by the inverse of the Lipschitz constant, which means that if the Lipschitz constant is growing, the step size is going down. So your algorithm is gonna slow down. So if we put together now these two properties of the landscape, and we look at the literature of distributed optimization, these are the conclusions that we can make based on the existing theoretical results. Given that the problem that we are solving is convex, but not strongly convex, the best we can get computationally from the existing literature is that the distributed algorithm will converge at sublinear rate, which can be quite slow if we compare with linear convergence, for example. But more importantly, if I look at the regime of interest, this regime where d divided by n is going to infinity, but statistically, I have enough samples to have an error here sufficiently small, in this regime, the Lipschitz constant is going to infinity, meaning that your algorithm is, the convergence rate, your algorithm is going to slow down. So at the point that is not going to be useful, okay? It's going to be useless algorithm. So you see what happens? We identify this seems to be the end of the story, because we identify a regime, this one under this condition, such that statistics tell us that we can make statistically consistent estimate if someone will give us theta hat. But on the computational side, if we try to compute this theta hat, the algorithm we get are highly inefficient, because they are arbitrarily slow. Okay? So that seems to be the end of the story. There is a mismatch between statistical guarantees and what computationally we can do. Is it clear, the issue? Any comment, any question? Okay, but given this gap, let's try to run some simulation to see, run simulations of existing algorithm to see what's going on, what happens. And then we can try to understand if there's an issue, what is the issue? Okay, let's call this objective function, the total objective function that we want to minimize, like theta has, f of theta. And suppose that you want to solve this problem in the centralized way. What would you do? You would run a projective gradient algorithm, right? If you want to focus on a first order method, which means what? That your theta at iteration t plus 1 is going to look like what? Theta times t minus a step size gamma times the gradient of the centralized function at time t. And then let me use this notation to denote the projection onto the L1 ball, okay? So this is a vanilla, it's the textbook projected gradient algorithm. The problem is that now if I want to do this on a network, I cannot implement this scheme directly because there is no way that agents can compute the full gradient, right? This gradient is the sum of the gradient of each of the functions. And agent I knows only its own function. So there have been several attempts to decentralize this projected gradient. And what I reported here is a simple, one of the earliest attempts called distributed gradient descent. And the algorithm works like this. Let me explain what it does. The algorithm says that given that I cannot compute the full gradient, and let's introduce, and I cannot implement directly this algorithm here with a common theta. So the idea is that let's create copies of this common theta. And so every agent owns one copy, theta I. So if this is agent I and this is agent J, this is going to be theta I at time t. This is going to be theta j times t, which are the two copies, local copies of this common theta. And now the idea is that we want that this theta will converge to a common value, right? Possibly eventually matching the trajectory of this algorithm, this common theta. So how to do that? Well, a natural approach would be, okay, let me interleave two steps in the update. A first step aims at, it's a consensus step, a step where I try to enforce that all the theta here, all the theta are equal. How can I do that? If I have two theta that I want to make equal, let me average them. Let me average this theta with this, and then so that they will get closer to each other, right? This is what the consensus does. And this is exactly what this step is. Every agent will get the theta from their neighbors. These weights are non-zero only for the neighbors of each agent I. So what every agent I does is first collect all the local copy from their neighbors and then average them. And the goal of this averaging process is to say, suppose that you have two, instead of using my theta t, I'm going to use an average between my theta and the theta of my neighbor. So I will gonna end up in some point, for example, in the middle, right? Or depending on how I choose the weights. And this is going to be my intermediate step here. And once I'm here in this point, what I do, I will try to mimic the behavior of the gradient algorithm, but I don't have the full gradient. I replace this full gradient with my local gradient only. Okay? Which means that in this picture, once agents will tend to agree on the local copies, they're going to move along their own local gradient minus fj of theta jt. And this one is going to move, for example, minus fi of theta it, right? And this is going to be the new theta I t plus 1, and this is going to be the new theta j t plus 1 after projection. So you perform this, and then you project onto the L1 ball. Is it clear, the idea of the algorithm? So you first average with your neighbors to enforce a kind of consensus. In general, you are not in the same point. You are in something like this, right? And then you move along your local gradient, and then you repeat the process again and again. So the idea is that the averaging will enforce all the theta to be almost equal to the common theta, and this gradient hopefully tends to mimic the behavior of the full gradient. Does it make sense? That's one of the simplest distributed algorithms.
Okay, sir. Got it. But I had a slight confusion. So the thing is, how are we understanding who are the neighbors of this particular model? Yes.
In general, you have a network, right? And then if this is I, this is J, and for example, you have another guy here. All your neighbors are those that are in your coverage radius. For example, for agent I here is going to be this, right? This is the neighborhood. This is agent, for example, node K. So agent I can talk to agent K and agent J. For example, in a wireless network, these are all the agents that are in your coverage radius, right? In your transmitter-receive coverage radius. In general, you need to have a protocol that tells you who are your neighbors, right? But let's assume that the network has been established. You have, for example, a wireless connection, and given the protocol that you are implementing for the communication, you know who are the agents who can receive your information. And I am assuming that whoever can receive, if agent I can receive information from agent K, also the other way around happens. So agent K can receive information from agent I. So does make sense?
Yeah. So if I understand, is it so that it can so happen that the neighbors are actually the geographical neighbors as well? So they are close together geographically, or is it not so?
Yes. In general, if you have a wireless network, very likely those that are your neighbors are also those that are closest to you, right? Because if you are wired connected, it's a different story, right? Technically, this can be a logic graph, not necessarily a physical graph. It really depends on the application, the scenario, right? But conceptually, these are logic neighbors, right? It's a graph of dependence. But in practice, very likely, if you map this into a wireless network, very likely this graph corresponds also to the geographical graph.
Okay.
And how far you go into the number of neighbors that you have depends on the coverage radius of your wireless communication, wireless system of each node, right? Each radio.
Okay, sir, got it.
Sure. So, and if I look at any other question, okay, if I look at the results, if I look at the existing results to, again, remember, this is the summary of what we know. Let's simulate this algorithm and see what happens. Let's see how close are the predictions that we get from this existing theory, if these predictions are confirmed by the simulation. Here's what the first simulation. And the first simulation that I plot the following. Here, I plot the centralized statistical error. This is, remember, it's basically this quantity here. The best you can achieve if I solve the problem, if someone will give me theta hat, so the statistical error, which is this line down here, okay? And then on what I'm gonna plot here on the y-axis is and by the way, sorry, this line up here is instead the statistical error of the same quantity if every agent solves the problem locally using only their own local data, right? So solve like a smaller lasso problem, the one using your own local data. As you can see the gap. If you don't communicate, you cannot achieve the centralized statistical error. So we need to fill this gap with an algorithm. And if you look at, so what we plot here is the average estimation error, so the distance of the local copy of each agent over the time, t, from the ground truth, the quantity that we want to compute. And given that there are m machines, I'm just averaging the error across the m machines, right? I consider each one, and I average across the machine. And this is a function of the iteration t. And what I plot is exactly this error here versus the time t, the iteration t here. As you can see, there are a few comments here to make. Maybe I can zoom. The first comment is that if you look at let's pick one curve, and then I discuss the different curves refer to different step size. Remember, your distributed algorithm here has a step size gamma, okay? So for each gamma, I have a different curve, and I will discuss this in a minute. But let's look at the behavior of each curve. This is a log scale, which means that a linear decrease like this means linear rate, linear convergence. So what we observe is that it seems that we have linear rate here, but not to an arbitrary error like going to minus to 0. But we have linear rate up to a threshold, right? For example, pick this curve. I have a linear rate, but only up to this threshold, okay? And this threshold can go down if I decrease the step size. So decreasing the step size, I go from this value to this one to this one. So this seems to say that actually we can achieve the centralized statistical error if we keep decreasing the step size. But in the moment that we decrease the step size to achieve this error, see what happens. I go from this curve to this curve, which means that the rate is going to slow down. So it seems that there is a kind of speed accuracy dilemma, meaning that if I want to achieve centralized statistical error, I need to decrease the step size. And in the moment that I decrease the step size, I'm slowing down my algorithm. So this phenomenon is not captured by the theory, first. Second, the theory predicts sublinear rate. Things are more complicated because actually we observe linear rate, not sublinear rate, but only up to a ball, to a threshold. So this is completely unpredicted by the theory. And this will explain the contradiction between the existing prediction and what we observe. Let's look at the second part, which is even more interesting. What happens? This is for a fixed day, this is for a fixed dimension D and N. What happens now if I look at the regime where D and N are going to infinity? But remember, this is the magic number. This is the ratio that controls the statistical error. So suppose that I increase D and N, but I keep this ratio constant, so that the statistical error is not changing, right? And if you do that, what we plot here, first for the centralized projected gradient, this is in the centralized case, I show that each curve corresponds to a different dimension D. I'm increasing the dimension, but in a way that this ratio remains constant, which means that the number of samples is growing in this way. For each curve is for a given D, and when I change D, I also increase the samples according to this formula, so that this ratio remains constant. And if you look at the curve, error versus iteration, you see you have three different curves here, and they have the same slope and the same statistical error because this quantity remains constant. As you can see, in the centralized case, we observe that the convergence rate is not going to change when I increase D and N so that this ratio remains constant. But if you look at, and this is the centralized projected gradient algorithm, if I instead look at the same result for the distributed version, the DGD, as you can see, these curves no longer have the same slope. You can see better here when I change the scale. This is the same picture. This is the same picture here, just changing the scale. As you can see, they have different slope, and the algorithm is going to slow down. This is the direction we are going when you increase D. Okay, this means that we are in a situation where it happens exactly what we were conjecturing, that if in the asymptotic regime, the algorithm is slowing down. Okay, is it clear the phenomenon, what's happening here? So your algorithm is becoming slower and slower in this regime, but this happens in the distributed case, in contrast with the centralized where this is not the case. So this is quite pessimistic results. Now, the question is that I present the simulation only for one algorithm, right? Not for all of them. This is a pathological problem of this algorithm, or what's going on if we implement other distributed algorithms? I don't want to make it too complicated, but this slide, don't worry, there's a bit too much math, but it's quite easy to understand at high level. This is a snapshot of the existing distributed algorithm, different approaches used to decentralize the projected gradient. We saw one example. The idea, without going into the math, at high level, the idea is that these different schemes, what they do is to implement a different way to estimate the local grade, the full gradient, the gradient of the centralized function, and a different way to enforce consensus among the local copies. We saw already this algorithm, this algorithm here, where if you remember what we say here is that what they do here, all the agents, this is agent I, agent J, they first perform a consensus pushing them close to each other, which is this step, and then they move along their own gradient, right, which is this step. You can ask also the question, why don't we do the other way around? Why don't we, and this is called combine, this scheme is called combine then adapt, because you first combine the estimate with your neighbors, and then you adjust, you adapt your direction, you along with you are going to update using your own gradient. That's why it's combine then adapt. You can do the other way around, right? You may think, okay, instead of doing that, this is agent I, agent J, let me first move along my local gradient. So I first do this, which will correspond to this, and then project onto the ball, and this is going to be this update. And then after doing that, I enforce consensus. I average across the agent, across my neighbors, and then I get this update, for example. I get this new point, which is theta I t plus 1, and this is going to be theta j t plus 1. And this was theta I t, and this is theta j t. Okay, so this scheme is called adapt then combine. So you first move along your own local gradient, and then after that, you average with your neighbors. Okay, is it clear, guys, what I'm doing here? Is it clear the difference between these two schemes?
Yes, sir.
Okay. Then there are but in both these schemes, as you can see, agents are always using only their own local gradient here and here to correct the direction, right? They are always switching the order of the consensus, first or later. There are more sophisticated schemes, including some that we introduced in my group, where basically the idea is, instead of using your local gradient, why don't we get some help from the network to estimate the full gradient? So instead of, look at this scheme, instead of performing the update, the local update using your local gradient, let's try to replace this local gradient with some vector GI, which is an estimate, sorry, there's a typo, this is J, with an estimate of the local gradient for each agent. So instead of using your local gradient, you're going to use now this vector G, which is a kind of estimate of the full gradient. And this estimate can happen, requires, I don't discuss now in detail the process to estimate this full gradient. All you have to know here is that using an extra step of communication, you can have a better estimate of the full gradient than what you can get if you use only your local gradient. This estimate is what we call GI. So this scheme, it does what? It's very similar to the ATC, with the difference that you first move along a direction that it's a less noisy version of the full gradient, and then you enforce consensus among your neighbors so that eventually these local copies will look similar to each other. This method is called the family of methods using this approach, meaning replacing the local estimate with something that it's less noisy, with a better estimate of the full gradient. They are called gradient tracking methods because you are trying to track the full gradient of the function. In addition to another variation of this method that still employ methods that employ a form of correction of the local gradient are primal dual methods. ADMM is an example, if you are familiar, if you heard of ADMM. These methods are of the same philosophy, however, of the combine then adapt. Because see what happens. You first do, in the combine and adapt, you do first a mix with your local neighbors, which is exactly what you are doing here. You are mixing your estimate with one of your neighbors. And then in the CTA scheme, you are correcting with your local gradient. Here, in the primal dual, you are correcting the direction with your local gradient plus an extra term. And this extra term is a correction of the local gradient that should be better than just using your local gradient. This is based on dual updates. It doesn't matter, it's a detail. There's a dual variable that basically plays the role of the correction here. But philosophically, this scheme looks very similar to this in terms of updating sharing only the estimate among the neighbors and not to the gradient. And the gradient is still correct, computed after the mixing. Is it clear the difference between this algorithm?
Yes, sir.
This one only local gradient. This one in maybe switching the order. Does first you mix and then you correct with your local gradient, or vice versa. This scheme do a gradient correction, estimating directly the full gradient. And this scheme also implement a gradient correction using dual variable. But the difference between this scheme and this scheme here is that in this scheme you are first move along the gradient and then you mix. Here you first mix and then you correct the direction using an estimate of the full gradient. Okay? Meaning that in this scheme you are not passing the gradient through the network. You are not sharing the gradient among the agents, which instead you do here. Okay? This is the key point. Okay. If that's the case, how do they perform if you run simulation? Here's the results. Let me comment a bit this picture because there are several interesting insights. Okay, the first picture here is obtaining for D larger than N and D and N fixed. We are not changing. And what we plot here is the estimation error that you can achieve once you have run your algorithm, you reach convergence, versus the local sample size. How many samples each agent has locally. As expected, when for D and N fixed, for D fixed, so sorry, N is not fixed, N here is growing because I'm increasing the local sample size, but we are still under the condition that D remains larger than N. Remember, big N is equal to small n times M, the number of machines. So as you can see, what this first picture tells us that we can achieve this statistical error is the one that you achieve in the centralized setting. So this tells us that no matter how many few samples we have locally, if we tune properly the algorithms and the step size and everything, all the schemes that I show you in these slides, all the schemes that we have here, they achieve basically all the centralized statistical error. Okay, and no matter how many samples we have locally, we don't need a minimum number of samples locally to achieve. Even if locally we have only one sample, we can achieve centralized statistical error. Okay, this is the interesting results, because it says that, oh, even if we are violating the information theoretical lower bounds locally, we can still achieve centralized statistical errors. How about however, what is different between these schemes is how many iterations, if you want, how many communication rounds do we need in order to achieve the optimal centralized statistical error. If you pick a number of samples in a statistical error here, you're going to read on this picture, on the y-axis, the number of communications rounds that I need. For example, 100 local sample size. If I want to achieve this statistical error, I need this number of communications for each of the scheme. Okay, that's the way to read this second picture. As you can see here, there is a significant amount of difference in terms of communications. Look at this. The axis here, we have to break the axis in, because we cannot cover all the orders in a single page. So as you can see, the CTA DGD, the one that this scheme here, the one that first average the agents, the iterates, and then correct using your local gradient, requires a significant amount of communication of the order of 2 to the power of 2 times 10 to the power of 5. If I go from the CTA to the ATC, which is this one, ATC does exactly the opposite. It first mix the gradient, first move along the local gradient, then it mixes everything through the network. So if I just switch the order, there is a significant gain, order of magnitude faster, just because I'm switching the order of these two operations. And if I look at the primal dual method, remember, philosophically is very similar to this scheme, because both of these, they have the fact that they are first mixing the iterates only, and then they correct locally with their gradient. This gradient is a better estimate of this one. These two quantities, this quantity is a better estimate of the full gradient than the local gradient only, which explain why primal dual are a bit better than just plain CTA DGD, but still its order of magnitude is lower than mixing the gradient through the network. Okay? And if I do gradient tracking, which is this scheme here, the gradient tracking is even better. So meaning that achieves the same, all these achieve the same statistical error, but much faster. The gradient tracking is much faster. One last picture here to show what happens when d divided by n is going to infinity. And remember, s log d divided by n remain constant, so that the statistical error is the same. So in this picture here, I plot the number of communications that I need to achieve the same centralized statistical error versus the dimension. Now I want to understand how the rate scales with the dimension, given the dimension is going to infinity. And this is a very interesting result. See what happens. The scheme that first average the local copy and then correct with the local gradient locally, without exchanging the gradient over a network, has a cost of communication that blow up with the dimension. It's linear. If I do ADMM or primal dual, same story, still linear, better slope, because clearly we are trying to use, instead of using just the local gradient, we are improving the estimate using the dual variable, which explain why the slope is different. And then if I look, however, at the scheme that the CTA scheme, the ATC scheme, the scheme where I'm mixing both gradient and iterates over the network, this one here, then as you can see, the communication, the number of communication rounds will grow only sublinearly with the dimension. No longer it looks like a log thing, right? And if I look at gradient tracking, it seems to be independent of the dimension. Okay, this is a very interesting behavior. Note that these are existing schemes, and nothing like this happens in low dimension. So these are phenomena appearing only in high dimension. There is no theory explaining this. We don't understand why there is this gap. And that's exactly the rest of the talk. I'll try to explain what's the missing phenomenon that the existing theory cannot capture and how to fix this, how to try to have an understanding of the behavior of these algorithms and why we have such a big difference, for example, like this, between these schemes. Going from a scheme that is completely useless in practice, this and this, to something that becomes a bit more reasonable. Is it clear, this picture? Any question? I think this is the most important. The rest it will be a bit more technical, but I think this is the big picture. There's a significant gap between theory and practice. We don't understand why, and I'll try to give you an answer in the next slides. Any question? Okay. How much time do I have, roughly?
We will be, so 1 hour will complete in 3 minutes, but sir, you can continue with your discussion. It's okay. We can have 15 minutes more.
Okay, so roughly say 15, 20 minutes. That's the time that I have?
Yes.
Okay. Okay, so what is basically the main idea? What are we missing what are basically in 20 years of distributed optimization, nobody studied this, what happens even for linear regression. So what's the missing part that the theory cannot capture? And I will explain this, and then building on this understanding, we will try to, once we understand what is missing, we will try to cope with the issue that the existing theory faces, and show what are the standard results if we account for this phenomena. And then I don't know if I have time, but I will summarize the theoretical guarantees of all the schemes that I showed you before at the end in a picture, in a table, so that we can comment the differences and why is the case that these schemes are so different in high dimension, while in low dimension they work pretty much. All of them are quite well. I mean, they work pretty well in practice. Okay, let's go back to the linear regression problem that we are solving. We said that if we have enough samples, meaning that if n is of the order of s log d at least, meaning that this quantity is small, we can control, we are sure that theta hat, the estimated solution of the lasso problem, is arbitrarily close to the ground truth, the quantity that I want. This is in general behavior that happens for strongly convex problem, not for convex problem, meaning that for strongly convex, when this quantity is close to the one associated to theta hat, also the argument, the minimizer that gives you this distance is close to theta star. But this function is not strongly convex. So how can it be that we can still achieve a result that has the flavor of a strongly convex function, of the minimization of a strongly convex function? The reason is that although it's true that theta hat, both vectors, theta hat and theta star, span the entire space. Remember, we are in RD. It's also true that theta star does not span the entire. So these are d-dimensional vectors, but theta star does not span the entire space, because remember, theta star is S sparse. Theta star is S sparse, meaning that only S components are different from zero. So this is in a low dimension, which means that it's in a low dimensional space. If you want a picture, let's assume that S is the support of theta star. Okay, meaning that theta star is the set of the subspace of the component of theta star that are non-zero. And let's call S complement whatever is orthogonal. So this is my subspace S, and this is S orthogonal, which means that over here, this is the set. The x-axis here is the set of all the vectors that are S sparse, okay, with the same support of theta star, which means that my theta star is going to be over here, right, in this set. What the lasso problem does, the main property of theta hat, is that although theta hat belongs to a d-dimensional vector, it does not span the entire space. If I choose the R sufficiently small, I can control the sparsity of theta hat, and I will have that theta hat is not really exactly as sparse as theta star, so does not overlap, does not belong to this space S, but it's roughly close, because I can make it almost sparse, meaning that my theta hat is going to be something that is inside this set, and very close to this S. So it cannot go everywhere in the space. And this is controlled by this region, this cone. This is the cone of so-called sparse direction. What this says is that theta hat has to be in this cone, if I choose R sufficiently small, so that the entire error belongs to this cone here. What is this cone? This cone is the cone of so-called sparse directions. It's the cone where is the set of all the d-dimensional vectors, all the directions, such that the amount of the mass. So this is the projection. This is a vector that has the L1 norm of all the components of the direction D belonging to outside the support of S. So these are the components that are outside the sparsity pattern of S. So the mass outside the support is smaller than the mass inside the support. This is what this says. In other words, this is a set of sparse directions, right? So what we learn from this, and this is something we can prove. We can prove that if R is sufficiently small, this error belongs to this cone of sparse direction. If this is a textbook result, if you can check any book of high-dimensional statistics and you can find these results. So if that's the case, in order to establish the results, we don't need strong convexity of the function everywhere. We only need strong convexity in this region. So we only need a situation like this. We only need that my function is carved, is strongly convex only in this cone, not everywhere else. And this is exactly what happens. With high probability, if I use for general data distribution, Gaussian, sub-Gaussian, and so on, I can prove that this is exactly the landscape. With high probability, my function remains strongly convex only in this cone. I will skip the math for this, but these are, and same story for the Lipschitz continuity of the gradient. In this cone, my function has a gradient that's Lipschitz continuous. So with a constant that does not blow up with the dimension. And these are mathematically is captured in some formula. I can skip for the interest of time, but basically what this formula are saying that the function is strongly convex on a restricted set of directions that are exactly this. And same story for the Lipschitz continuity. I will skip the detail because there is no time, but it's just a mathematical translation of this property. Again, this is something you can find in any book or high-dimensional statistics. So given that now we know that my function is strongly convex in this cone and also L smooth, if I want to design a fast convergent algorithm, meaning that having linear rate, because we are using only first order information, we cannot aim for more than linear rate. The idea is quite obvious, right? I need to make sure that any distributed algorithm will travel in this cone, in this region of the space, so that the trajectory of my algorithm will experience basically a strongly convex function, roughly, because I may not be able to stay exactly into this set. But the idea is I know that there are some directions where my function is good. Let's try to drive the algorithm to stay within that region. That's the intuition. That's the idea. And I cannot do, let me skip some other details. So, but now the question is that these are some open questions. So, are the trajectory of different distributed algorithms compatible with this cone? What do I mean by that? I mean that, are we sure that we can control, we have enough degrees of freedom when we are in a distributed setting that locally agents can control the full trajectory in order to stay within this cone? This is the question. And the answer is no. In fact, that's exactly the reason why the algorithm behaves so differently, because depending on how we implement the update and how we use local information, we may generate different directions. Some of the trajectory may be controllable, some others may be not. And that is going to be exactly the question. So understanding what are the key properties that we want from our algorithm in order to be able to control this trajectory. And second, suppose that we can do that for some algorithms. How can we do this in a distributed way? Because every agent does not have knowledge of the entire landscape of this function, can only see its own gradient and maybe information from the neighbors. And what's the role of the network? Clearly, if I have more samples, I skipped the details of the restrict strong convexity and smoothness, but if I have more samples, this function becomes strongly convex in a larger set of directions. So if I have more samples, it's easier to have strong convexity. But if I don't have samples, the idea is that can I use communication to rebuild the landscape? So it seems that there is a trade-off between how much communications I want to spend and how many samples do I need. Okay? These are all open questions. Let me try to explain. So I think I have maybe 10 minutes now or a bit less. So let me try to explain quickly what is the result for one algorithm, and then I'm gonna summarize the other algorithm. So just I want to give you now what is the mathematical. Let's close the loop now. I gave you simulations showing that they may perform decently well, some of them. Let's try to make it this formal. But the idea is exactly here in this slide. We want to tune the parameters and control the trajectory in order to exploit this restricted strong convexity and smoothness. Okay? Is it clear at high level? Any question? Okay. So let me pick the gradient tracking algorithm. I already discussed quickly the algorithm. I don't go into details for the interest of time. I just remind you what we want to do. Every agent has a local copy, theta I, t, and what every agent does, remember, first they move along. It's a projected gradient algorithm, but given that agents do not know the gradient of the full function, they only know they only know the gradient of their own local function. Here, the idea is to estimate the full gradient using this vector G. Every agent try to estimate the full gradient and move along this estimate. After doing this update, like this and like this, for two agents I and J, basically there is a consensus step, meaning that they average this information, they generate a new point, and this is going to be my theta I t plus 1, right? And this is theta j t plus 1, okay? And which corresponds to this step. And then the gradient tracking needs to be updated because the gradient over the network is going to change, right? Because the point is changing. And I will skip the details on how this is done. There is a mechanism to do this. For those of you who are familiar with consensus algorithm, this is a dynamic consensus method. You can find details in this is one of the first papers where we introduced this idea. There is no statistics there, but the reason why this mechanism works, it's there. So if you are interested, you can look at those papers. And in one of my recent papers here. This is the algorithm. What can we say about the statistical guarantees? Suppose that we are generating data according to a Gaussian distribution, meaning that each row of the data matrix is Gaussian distributed with covariance metric sigma. And let's assume that all the rows are IAD. Noise can be sub-Gaussian. We can even extend this to sub-Gaussian. It's not a big deal. And keep in mind this magic number. This is the condition number of the covariance matrix. So meaning that this is, if you want, is the condition number of the population function, the function when you have infinite data. If you have infinite data, your objective function is going to become strongly convex everywhere, and this is the condition number of the strong, the ratio between the Lipschitz constants and the strong convexity constant. Okay, it's the covariance, it's the condition number of your covariance matrix of the data. It's a quadratic problem. So, but it's like you can interpret like the best you can get. It's the best behavior of your function if you have infinite number of data. Okay, and under the assumptions that the statistical error is controllable, this is the same results that we have, remember, in the centralized case, statistical consistency. If we have enough samples given the dimension, so the statistical error is small. Let me skip the other condition. I will come back to the network condition later. Then this algorithm works in the following way. The distance of each local copy from the ground truth, if I average this distance will decrease according to this formula. What does it mean? There is a term here, lambda t is the iteration number. So lambda is a number less than 1 under the assumptions here. And this says that this quantity is clearly going to 0, right? Because when t grows, this is lambda to the power of 3. So what this says is that this error is decreasing, but at a geometric rate, but not to an arbitrary, not to 0, but to a ball. This. So what this says is that if this is my theta star, this is my ball, this is the ball here, is this quantity here. So what this picture says that we have linear convergence of the trajectory, but not to a point that is arbitrarily close to theta star, but only up to a ball. And the ball is of this order, okay? This is what this says. So we are now predicting a linear convergence up to a ball. Let's look closely at these two quantities, the rate and the ball, to understand if they are optimal or how good or bad they are. Okay? If you look at the rate, let's look first at the rate, the expression of lambda. Lambda is given by this quantity here, but in particular, let's look at the first term. The first term is 1 minus 1 over 2 kappa. Kappa, remember, is this condition number. What is this quantity? For those of you who are familiar with the convergence of the projective gradient algorithm, this is the convergence rate of a centralized projective gradient algorithm applied to a population function. So if you have an infinite number of samples, this is, and you apply a gradient algorithm in the centralized case, this is the rate that you get. This is the best you can achieve if you use first order methods. The problem is that in practice, our rate cannot match exactly this because we don't have infinite number of samples. So there is a degradation in our rate, which is captured by this second term. But the interesting result is that this second term basically depends on this ratio, which is sufficiently small, which means that what this says is that this is the price to pay because we are not strongly convex everywhere, and because we are using a finite number of samples. But this term is sufficiently small, almost negligible, which means that we have a rate that is almost matching the one of the centralized system with an infinite number of samples. And then basically, more importantly, the other interesting results that we have from the rate is that, remember, we are in a regime. Let's see what happens to the rate when N and D are growing. And the ratio, this ratio remains constant, meaning that the number of samples is growing like this. If this ratio here remains constant, this quantity remains constant, this quantity remains constant, which means that the rate is not going to change. This is a very desirable result. We want a rate that as long as the statistical error is not changing, I want to be able to compute this statistical error with a rate that also is not changing as long as I have enough samples. Even if D grows, even if the problem becomes more complicated, I'm not going to lose on the rate. And this is exactly what we observe in the numerical results. If N and D are growing, and the total number of samples in the dimension in a way that the statistical error remains constant, you see what happens to the rate. I have different curves, but they have roughly the same slope. And they are all sitting around the same statistical error. So which means that the numerical results are really matching our theory. Okay? One last comment. What about this condition here? What is this condition here? This condition says that rho is, I don't have time to go into details of rho, but rho tells me how fast the network mixes information. Rho is a number between 0 and 1, depends on the network topology and the weights that I'm using in the consensus update. And what this condition says, roughly speaking, is that this condition says that the network this quantity should be sufficiently small, inversely with the number of agents and the condition number. This says that the network should mix information sufficiently fast if I want to achieve centralized statistical errors. Okay? That's what this says. This condition may be true or not. If the network is very good, meaning that almost fully connected, this condition is going to be true. Because when you have a fully connected network, rho is equal to 0. When the network is weakly connected, rho gets equal to 1. Okay? These are the two extremes. If you have a disconnected network, rho is equal to 1. If it's fully connected, meaning that everybody can talk to everybody, it's going to be equal to 1. Sorry, it's going to be equal to 0. So it requires that the network has to be sufficiently connected. If this condition is not true, I can enforce it running multiple rounds of communications per gradient update. I don't go now into details, but this will translate in this result. It will translate in this property that if this condition is not true, I can enforce it if I run this amount of communication per iteration. And if I put this together with the linear convergence rate, this is the final results that I have. It tells me that the total number of communications that I need to achieve a solution that is statistically optimal, an epsilon neighborhood of a statistically optimal solution, is of this amount. As you can see, this part is pretty much the one that you have for a centralized proximal gradient. Now there is a degradation, is 1 over 1 minus rho, which is due to the network. And then there is this other log term that, however, does not depend on the dimension. So this explains basically this picture. If you remember when we plot the total number of communications versus the dimension, we have that, if you remember the picture that I showed at the beginning, for the gradient tracking, this is almost independent of the dimension. This is exactly what this formula is saying. There is no D here, no dimension. Okay? Maybe just 2 minutes and then I can conclude. What happens to the other algorithms? What is the take-home message? If I put in the table, I think that this is all you have to remember at high level. And now we'll quickly go. Just give me 2 minutes and I think I can conclude in 2 minutes, just to give you the big picture. So here we can summarize, we can redo the same theory, use the same theory that I developed previously, exploiting the restricted strong convexity and smoothness, and obtain the behavior for all the other algorithms. And here is the entire take-home message. We are in a regime, remember, we are in this regime, we are interested in understanding how many number of communications do we need to achieve an epsilon optimal solution, and how this number scales with the dimension and the data when the statistical error is not changed, okay? And the message, the interesting message is this: if I want to achieve this result from the scheme, the DGD CTA, remember, DGD CTA is the scheme that mixes only the iterates, first and then correct with the gradient. We need to choose a step size that it's inversely proportional with the dimension. No matter how good is the network can be arbitrarily good, but the step size is going to depend on the dimension. And because of that, the overall rate, because of the dependence of the step size from the dimension, inversely from the dimension, the number of communication is going to blow up with the dimension. There is no other way. This is a consequence of this choice of the step size. It doesn't matter how good is the network. We have a similar results for a primal dual because philosophically it's a similar scheme. It always mixes only the iterates, never the gradient. And then still the step size should be inversely proportional with the dimension, which will determine for a primal dual scheme, a rate that blows up with the dimension, which is, I think I have a picture. No, I don't have it here. Again, it's the same picture that I showed you before. Is this one? This will explain these two curves. If I go for a scheme where the DGD ATC, where I mix gradient and iterates with my neighbors, I can free the step size. The step size can be chosen constant, independent of the dimension. I only need a network that depends on the dimension. Inversely, the connectivity of the network should be good. The network should be sufficiently good. But if I enforce this condition with multiple rounds of communications, this will translate only in a logarithmic dependent on the dimension. You see, there's a log D term here. And this explains why here I have a logarithmic dependence with the dimension. Okay? And then we have the gradient tracking that I showed you before, where the network depends only on the edges, not the dimension like here. And because of that, I don't have any dependence on the dimension here. So the overall take-home message, and this is the summary, is that I can skip the simulation. The simulations will confirm the theory, meaning that if you break those conditions on the step sides, you are not going to be able to achieve centralized statistical error. But the take-home message is the following. What we learn, which is a new result in high dimension, it happens only in high dimension. The result says that in high dimension, given that the function is not strongly convex everywhere, the direction that each algorithm is using to perform the update matters a lot. And the key point here is that if agents will share with the neighbors only the iterates, only the local estimate, and not the gradient, the number of communications will depend on the dimension. Because the only way to control the noise of the gradient, on the gradient, you can interpret the gradient like a noisy version of the centralized gradient, is to use the step size. And the step size should scale with 1 over D. This is exactly what this is saying, right? 1 over D and 1 over D. Because you don't have any other leverage to kill the noise from the gradient than using the step size. If you pass the gradient over the network, you can use the network to kill the noise coming from the gradient, the fact that you don't have the full gradient. And then you use the network connectivity to control this noise. And because of that, you can have a better dependence of the dimension for the scheme, the ATC, or an independent, or a rate that is completely independent on the dimension. So, and this is pretty much, I think, the message. There are several other directions that we developed, but I don't have time to discuss them. And what the take-home message at the end is that if you want to really design algorithms, that the optimization algorithms for learning problems, you really need to bridge statistics and optimization. You cannot look at the convergence. For example, you cannot study convergence analysis of distributed algorithms or even centralized algorithms just looking at the optimization problem. This is not our ultimate goal. Our ultimate goal is the statistical estimate. So you need to combine with statistics. And I gave you an example here for the distributed algorithms. After 25 years of distributed optimization, we were not even able to understand sparse linear regression, just because we didn't combine statistics and optimization. So that's my message for you. If you want to work on machine learning problem and optimization algorithm for machine learning problem, you need to merge these two components. It's an interdisciplinary effort. And with this, I think I can conclude. So sorry, maybe it took more time than what I was supposed to do. So thanks for your time and attention. I'm happy to take any question.
Any question, please ask.
I had a question, sir. So one thing is that I was thinking that how much this concept is kind of implemented in edge devices, because edge devices require low resources and there are time constraints. So how much this technology has been adopted in the real world?
Okay. Which technology you mentioned? So you mean if you apply to where?
Yeah, so basically these concepts, how much of these are actually being applied, or are they in the research phase as of now?
Okay, good point. Okay, yeah, I think that the algorithms are pretty simple in terms of computation. I mean, there are a few things to consider. So I think that there is still an issue here that does prevent to be applied to the real world. And actually, let's say two, but one, I think we know how to cope with it. The second one is still under research. The problem is the following. First of all, computational, these schemes are quite simple, right? Because you need to just compute your local gradient, and once you identify your neighbors, you need to just communicate with your neighbors in averaging. So computationally, these are not very demanding as long as you are able to compute your gradient. But your gradient may depending if you do an online. I discuss here a sample average approximation. I discuss the stochastic, the online version. But if you do a sample average approximation, the first challenge is going to be that to compute this gradient, you may need to do one pass over your entire data set. If you have a large data set, this may be not affordable every time, which means that you need to use some variance reduction method. And this is something that I have not discussed, but you can incorporate variance reduction, okay? This is the first comment. But more importantly, the second one, which in my opinion is the big, because this is like a computational aspect that if you have enough, now with the multi-core machines that we have, or if you have enough storage, computing, let's assume that you can afford to compute the gradient locally. The major issue that all these algorithms have, and not just these schemes, in general, even in the federated learning, right? In all the literature, is that when you are in high dimension or very high dimension here, don't forget that every scheme here has to exchange a vector of dimension d at every iteration. So here you need to exchange the gradient and a vector of dimension, the thetas have dimension d, or here even the gradient, right? I didn't discuss in detail this scheme, but here you have two rounds of communication. One to update the theta and one to update the g. So this will cost you of the order of d. If we are talking about millions of variables, or this is the major bottleneck of all these schemes in practice. So if you want to make this implementable on existing technology, we need to introduce some method that avoids. We need to study the behavior of these algorithms when you don't communicate your entire vector D, or you perform some form of compression. What is the problem? So you can quantize and so on, but be very careful, because there is a misleading, in my opinion, a misleading way in many of the existing. There has been in the last 3-4 years, there has been an explosion of method doing compression, any form of compression and quantization in federated learning. when they show that if you do some thresholding like top K components, or you define an operator that compress the information, but unfortunately, all these papers are kind of misleading in my opinion, because they show that you can gain something in terms of components that you communicate. You don't communicate the entire vector D, you communicate less. But all these methods are done for a given D, for a fixed D. In the moment that you want to understand how the results will scale with D, all these methods requires a number of variables to communicate that is proportional to D. It's still linear with D, which means that you are not gaining anything. The gain it's just a false gain, because there are in fact lower bounds showing that you cannot communicate less than D, proportional. Of course, it can be a constant factor of D, which is still a small improvement, but if you want to understand the scaling with the dimension, it will be still D. I mean, it doesn't matter when you have millions or billions of variables. If it's 1 billion or half a billion, it doesn't make a big difference. So in terms of scaling, so which means that the main question to answer you made a very good point. If we want to implement this, bridge the gap between theory and practice and make this implementable, we need to do one step further. Once we understand now this behavior, we need to basically try to design methods that requires a communication cost at every iteration that scales sublinearly with the dimension, not linear. And this is an open problem. And I can tell you why it's an open problem, because if you look at this result, you see my mouse, right? Yeah. If what we learn from here, the communication cost is what? Is the product between if you want the communication cost, let's say C, is the product between the number of iterations or number of communication times the number of components that you per communication, right? The number of variables that you communicate every iteration, right? Now, this number here is D, because every time you communicate the entire vector, right? This number here is what you see in the table here. So as you can see, there is an interesting open problem here, because on one hand, so if this quantity depends on D, the overall communication cost is going to scale with D squared, because there is a D over here and another D from here. You understand what I'm saying? So here there is a D and here there is a D. So if you use these two methods, you're going to get a D over here times D here. So the total communication cost, your wireless system, for example, has to transmit D squared variables overall to compute an epsilon solution, a statistically optimal solution. In other schemes like this, it's going to be D log D or D log N, which means that, but we need to exchange the gradient to do that. So there is this kind of dilemma. On one hand, I would like to communicate the gradient, because if I communicate the gradient, this quantity becomes independent on the D. But in the moment that I communicate the gradient, I still need to transmit D. And the problem is that if I try to compress, because you may think about, okay, I need to estimate a parameter that is sparse, right? So the real parameter the real dimension is not D, it's S. So why I cannot compress? Yeah, if you don't communicate the gradient, you can compress. If you don't communicate the gradient, you are in this scheme or in this scheme, which means that you may save something here because you are compressing, but you get a D from here. So the total communication cost is going to be still D, because you get D from here and here. You understand what I'm saying?
Yes.
So if you want to avoid a D here, you need to remove, you cannot consider this scheme, and you cannot consider this, and you cannot consider this. If you want, you can consider just this because it's a log D. Let's assume the log D is acceptable. Or you can consider this. But in the moment that you are doing this, these two schemes are communicating the gradient. So the gradient is not sparse, even if the parameter is sparse. So which means that you gain a D factor from here, you no longer have a D here, but you're going to have a D here, because when you cannot compress something that is not sparse. You understand what I'm saying?
Yes, sir.
So it means that there is this dilemma. And we are research. So the open question is, can I design in high dimension, taking advantage of the fact that my signal is sparse, can I design a distributed algorithm that has a communication cost that is not proportionally to D, but sublinear with D? This is an open problem. I have a new PhD student who just joined my group, and he's working on a scheme now that seems to break this this impossibility result. And the reason is that we need to go beyond consensus. We can no longer use consensus, because here a key reason why we obtain these results is because we are mixing information. So we need to communicate. We need to avoid that. And we are now building a scheme that hopefully will achieve a logarithmic communication cost, but there is no free lunch. In order to achieve this, you need a condition on the local sample size. You need enough samples locally. You see the trade-off? If I want to save communication, I need more samples locally. If I don't have enough samples locally, there's no way that I can achieve a communication that does not scale with data. So this is exactly one of the fundamental trade-offs that I was mentioning at the beginning of the talk, like open questions. There is a lot of work to do in that context. So the technology, your question, so can I implement this? The real world, the existing technology will set some constraints on what I can transmit, what I cannot in terms of dimension and so on, right? And this will inform the theory that now we have a constraint that we cannot go, this dimension is too much. We need to have something more efficient. And closing that gap is still an open problem. Sorry, long answer, but yeah.
No, sir. I got it. Thank you. Thank you so much for your answer. So one announcement for the participants. So the attendance form link has been shared in the chat. So you will have to fill it. So please fill it within the completion of this event. And another thing is, sir, thanks a lot for your contribution in this presentation. Now, if you would allow, then we all would like to open our cameras and we can have one screenshot to like materialize this moment that we have to do.
Sure, of course. Should I stop screen sharing?
Yes, sir. You can stop screen sharing. And everybody, whoever can open your cameras, you can just turn on your cameras for a brief moment.
I'm having a little doubt, sir.
Yeah, you can ask it. You can ask it.
Sure, of course.
Sir, what type of environmental variables that has to be considered while we are defining step size in a local gradient function to improve the learning rate, sir?
Sorry, I don't understand what I cannot hear you very well. Say, can you speak maybe not too close to the microphone, because it seems to me that it's a bit, your voice is bumping, so I cannot hear you very well. Can you repeat your question, please?
I mean, to improve the learning rate in defining step size of local, while we are defining local gradient function, we have to define a step size, right, sir? So how, what type of environmental vectors that we can define to improve the learning rate of the network?
Sorry, I cannot understand your question. Sorry, I cannot hear you well. Okay. Can you? Is there anyone else who can hear the? It's not your. It's just the volume that it's like there's some distortion, so I cannot. You are. I mean, the way I hear is, but you're saying that. I understand that you're talking about the learning rate, but so you're saying that. So I say the learning rate in some algorithms should scale inversely with the dimension. In other algorithms, it doesn't. Right. So that's the result. What's your question about what you're saying?
Okay, sir. Okay. It's fine, sir. It's fine. Thank you.
No, please try again.
Batula Murali, you can do one thing. You can write your questions in the chat so that we can
sure.
read
That would be great. Or just speak not too close to the microphone. It seems to me that your volume there's a kind of saturation. So
yeah, the voice is, so it is cutting in between, so it's better.
But if any of you was able to understand the question, if you can repeat for me, I would be happy to answer. So
yeah, actually we were also hearing that distorted kind of a voice.
Okay.
So Murali, you can write the question in the chat, and in the meantime maybe we can all open our cameras, whoever can do that, so that we can have a screenshot. So everyone please turn on your cameras.
like closed. Okay.
So we have got the screenshot. Thanks a lot, everyone. So we will just wait for a minute for Batula Murali to complete his question. So maybe in the meantime, Asim, you can conclude the session and then we can take on the question.
Which
Okay.
variables can affect?
Okay. So thank you, Dr. Gesualdo Scutari. I, Asim Asrar, on behalf of IEEE Space Society, ITKG, would like to thank you for your insightful thought. Meanwhile, I just want to share my screen to present the virtual movement too, and we'll send a physical copy of this movement too later on. Is the screen visible? So this is a
Thank you.
small,
Thank you so much. Very
small
kind.
gratitude from the Society of ITKGP to you, Doctor.
Thank you. Okay, let me see the question. The question says, which environment variables can affect on learning rate while we are defining step size in local gradient? Okay, so the variables that will, the step size is going to depend, because the idea here is that we want to match the rate of the centralized, the statistical error in the centralized. So, if you do the analysis and you try to match this error, you will see that in the schemes where the choice of the step size depends on the algorithm. So the dependence of the parameters in the step size, how to choose the step size, depends on the specific scheme. The two families are algorithms that are not exchanging the gradient over the network, like the CTA DGD or the primal dual, and schemes that exchange some form of gradient, local gradient, or an estimate of the full gradient through the network, like the gradient tracking scheme or the DGD ATC. In the scheme where, just to give you, how should we choose the step size? What's the rationale in the choice of the step size? You can see, you can do like this. You can interpret the form maybe I can. Can I reshare this? Do you have a minute? Do I have a minute to answer?
Sure, sir.
Yes, sir.
So, okay, let me share again, because I think that this will help to, I tend to write, otherwise. Okay, so you can interpret once you do consensus, let me simplify a bit of thing. When you do consensus, what can you do? You can interpret like, let's forget for a moment the projection, right? Just I want to give you only the intuition. What do? You do something like this. You do the average with your neighbors. And then you have the step size here, the learning rate. And then you have the local gradient, right? Let's do this, right?
Yes, sir.
Now, you can rewrite this local gradient like the full gradient, the one that you would like to have, right? Plus an error like time t, right? You can write like that. It's like, so which means that you can now basically, you can rewrite this scheme like a stochastic, if you want a noisy gradient, right? It's like, let me move this here, up here, okay? So now this becomes like a noisy gradient. So you can rewrite now, suppose that the consensus is working. Suppose that you have enough mixing. So roughly, let's assume that these are roughly the same for all the agents, right? So this becomes like theta t, the same for all the agents, minus, let's say, gamma nabla f. Again, this is roughly theta t because they assume that consensus is working. And then you have minus gamma yeti, right?
Yes.
Now, this term is exactly it's a kind of approximation of the centralized gradient algorithm, right?
Yes, sir.
So, and you are happy with this because you cannot do better than that if you have all the data. The problem is that now you need to control this error.
Yes,
if this error is not controllable, then you are blowing up. So, which means that, and what is your leverage to control this error for this specific scheme, for example, that uses only the local gradient? Well, it's the step size, because you need to make sure that this quantity, it will be big O1, will be constant, right?
Yes, yes.
And if you look at the specific error, what is this error E? This error is exactly the difference between the global gradient and the local one, right?
Yes.
And if you look at the norm of this error, this is so the nabla f I theta minus nabla big F theta. This error is of the order of 1 over d. Sorry,
Okay.
sorry. It's big O d, which means that if you want that gamma times d is equal to a constant, you need to choose gamma of the order of 1 over d. Does it make sense? So
Okay.
the main reason why the main dependence, of course, there are other dependencies, like, because now I oversimplify. But you understand also that in the moment that if I want to improve this, there is nothing I can do with the network, because this is already the best case scenario when the network is very good. Suppose that it's fully connected, so which means that rho is 0. You are mixing in one step, you are averaging all the agents. This is the best you can do, right?
Yes.
You cannot do better. So which means that even in the best case, in the best network you can think of, this algorithm by construction has only the step size here as a leverage to control this error. And that's the reason why the step size mainly depends on the main bottleneck in the choice of the step size is this reason. You can interpret like a stochastic noise. So to control this noise, you need to choose gamma like 1 over d. There are other parameters, but they cannot help to fix this issue. The only way to fix this issue is if you use a different mechanism to generate this error.
Okay.
So, and now you understand how different algorithms will have different errors, right? Because if you average also the gradient, not just the iterates, but if you average also the gradient among your neighbors, you can understand that this error may be better, right? Because I'm reducing the variance, right?
Yes.
Or if I do gradient tracking, I have a parallel mechanism to control this error, to kill this error. So meaning that this error, if I have gamma epsilon t, if I have another mechanism that will force this to 0, I don't need to choose gamma to control this error, right? I can use gamma constant, right? Because if that's the case, this still go to 0, right? And this is exactly what happens in gradient tracking. In gradient tracking, the extra mechanism that I use to estimate the full gradient will drive this error to 0, so that I don't need to use gamma to go to 0 when the dimensions are growing. Does it make sense?
Okay, sir. Okay.
Did I roughly answer your question?
Yes, sir. Yes, sir. I understood, sir. Thank you, sir. Thank you very much.
Thank you. Any other question?
So it looks like we are at the end of the event, so there are no questions. So if any participant has any more questions, then they can just mail us and we will take it on with
feel free, any of you, to contact me. You have my email, right? So you are free to contact me to share if you have any comment, any question, even if you are interested in some of these topics and you want to learn more. Of course, I will be happy to collaborate with any of you. I mean, always interested in sharing ideas with students. So feel free to contact me.
Okay, that's even better, sir. That's great.
Thanks so much for inviting me. It was a pleasure to be with you. Yeah, and thanks for.
And it was great to hear you, sir.
So long.
Thank you, sir. Thank you very much.
Thank you.
Thank you so much, sir.
Bye. Good evening.
Thank you, everybody. Have a good day.
Bye.
Good night, everybody from India.
Bye.